Hello, I am Mónica Delgado. I am the Associate Director of Outreach at the Department of Mathematics at The Ohio State University. Our outreach program is called Buckeye Aha Math Moments, BAM. As part of our activities, we do summer programs, classroom visits, science fairs, and all sorts of activities to increase the awareness and appreciation of mathematics. Check our website and follow our social media to keep updated on what we are doing. Thank you for watching. Today I am going to demonstrate an activity you can do in the classroom to talk about the concepts of solids of revolution or rotation and the relationships between 2D and 3D shapes. This is not part of the Ohio standards, but it is part of the high school Common Core standards through the standard called Visualize Relationships between Two-Dimensional and Three-Dimensional Objects, which is described as identify the shapes of two-dimensional cross-sections of three-dimensional objects and identify three-dimensional objects generated by rotations of two-dimensional objects. We are going to focus on the second part of this description. Oftentimes, the difficulty in grasping mathematical concepts lies in its abstractness. Geometry provides a great opportunity in that we can visualize these concepts and oftentimes make crafts or objects that allow us not only to visualize it but also to touch the object and have a better approach at the concept. A surface of revolution is a 3D shape that is created by rotating a shape around a line. For example, if you rotate half a circle 360 degrees around its diameter, you get a sphere. And rotating a rectangle gives a cylinder. If you only rotate the outline, like in the previous examples, you get a hollow shape, which is why it is called a surface, only the crust, not a solid. If you include the inside of the 2D shape, like here, you get a full solid, a solid of revolution. This type of paper craft, called honeycomb, is great for crafting solids of revolution. Rotating half a 2D bell gives a 3D bell. These crafts are also culturally significant. In Mexico, where I am from, these are popular traditional decorations for the winter holiday, with shapes like bells, lanterns, and piñatas. For this activity, you will need scissors, glue, and several sheets of paper. It looks nicer if you use color paper, but scrap paper or copy paper works just as well. The traditional decorations I mentioned before use tissue paper, but since that is more fragile, I recommend not using that type the first time you do the craft. Let's start with the cylinder. Since the cylinder comes from rotating a rectangle, we need to cut several rectangles of the same size. You can use this opportunity to have students practice their skills at drawing polygons of given sizes. But honestly, that takes too much time. For practicality reasons, instead of doing that, I folded my sheet in half 3 times to divide it in 8 equal parts, which happen to be rectangles. This way, I get 8 equal rectangles out of each sheet. Feel free to try something different. Don't go too small though, as crafting will be harder. Anything bigger than my 8s of letter size paper will work reasonably well. As for how many rectangles you need, it depends on the size of your rectangles and the thickness of the paper. For this size and type of paper, 40 rectangles will do. You will notice if you need more rectangles later in the process. Alright, so after I cut my rectangles, I drew its outline on a piece of paper. Now we need to mark 4 horizontal lines across the rectangle. These lines should be more or less equally spaced. It doesn't need to be very precise. If you have a ruler, you can go ahead and use it. I don't have one at hand, so I'm just going to eyeball it. Here's another opportunity for your students to practice their math skills, as dividing in approximately equal parts without measuring is certainly a good math skill. Notice how I am leaving a smaller space between the edge and the first line. This is not necessary, but I think it gives the craft a nicer look. Then I try to copy the same distance between the lower edge and what will be the last line. Then I just make 2 marks dividing the space between the first 2 marks in 3 approximately equal parts. Since I don't have a ruler, I'll use a book as a straight edge. Make sure the lines extend outside the rectangle and mark them with 1 and 2 alternatingly. Next, we put one of our rectangles inside the frame we drew and put a line of glue on it along the 1 lines, like this. Now put another rectangle right on top of the first one and make sure they're glued along the 1 lines. With the second rectangle, we are going to put glue on the 2 lines and again put a third rectangle on top. Make sure the stack is always aligned with the rectangular frame you drew. Next, we do the 1 lines again and after that the 2 lines. We keep going, always alternating 1 and 2. Since I am alternating my rectangles in 2 colors, you can see that every time I have a red, I use the 1 lines, whereas when I have a yellow one, I use the 2 lines. So I can mark the lines with the colors as well, which will hopefully help not to make mistakes. Disclaimer, I did make mistakes despite my color code, but hopefully your students will be paying more attention than I was. Once you have all your rectangles glued together, we now want to bind them on one of the sides, the axis of rotation. For that, you can use a stapler or needle and thread. The stack is likely going to be too thick, so you might need to use a thicker sharp point, like a thumbtack. Once you manage to punch through all the rectangles, pull the thread through and make a loose loop. Make sure it leaves a space for the little booklet to open up. A loop or a staple on each corner will suffice, but feel free to add one more binding point in the middle of that side. Now we are ready to start rotating. Open the stack up on the unbounded side. You should see a design similar to this. Glue tends to be sneaky, so you will more likely see that the paper ends up glued in parts you didn't intend. Review the craft and make sure you have the right pattern. If you alternated colors like me, 2 rectangles of the same color should not be stick together at any place. No more than 2 sheets should be glued together in any point. If you see issues like that, just gently pull them apart. It should be easy since it was most likely just a tiny amount of glue that got in there unintentionally. At this point, if your little booklet doesn't open up to complete a full turn and reach the other end, then it means you need to add more rectangles to the stack. Now you can see the rotation magic. A cylinder from a rotating rectangle. In theory, when we rotate a shape, the shape leaves its trace, a copy of itself on every point it passed by while rotating, thus originating the 3D solid. An infinite amount of rectangles coming together to form the cylinder. Here, though we only have so many rectangles, we bind them together to fill in for the missing ones. At this point, we could simply glue the two rectangles on the ends and keep the cylinder, but we would lose the rotation fun, the capacity to really illustrate the concept once and again. So what I suggest you do is you glue some cardboard rectangles on the two ends to make it sturdier. The cardboard also makes it easier to grab the ends to perform the rotation. You can use paper clips to temporarily hold the cylinder together without losing the ability to go back to the rectangular form. Keep in mind that it is the opening process that really illustrates the concept. The cone and the sphere follow very similar steps. For the cone, we need a right triangle, of course. Again, to make my life easier, I folded a letter-size sheet of paper twice in half on the long side, and then one last time in half, but this time on the short side, so that I got again 8 equal parts, but these are thinner and longer rectangles than before. Then I used just a postcard as my straight edge to draw a right triangle using one of the right angles in the rectangle. Cutting along that line, I get 8 triangles at once. Even better, with the leftover paper, I just need to cut here to get another set of 8 equal triangles. How's that for practicality? 16 triangles from 3 folds on a single sheet of paper. Again, I trace the outline of the triangle on my working sheet, and I need to make 4 equally spaced lines again. You can probably see that I am using the same sheet as before, and I just erased the rectangle. But it looks like I can reuse the horizontal lines from before, so I'll do that. Those lines look very well distributed on my triangle. Just like before, I start by putting a triangle inside the frame and put glue along the one lines. Second triangle, glue along the 2 lines, and so on and so forth. Again, I can use a color code, taking advantage of the fact that I am alternating colors with my triangles. Once more, I put a string loop through each of the corners on the rotating axis, which I want to be the long side of the right angle. Lastly, I glue a couple of cardboard triangles on the 2 ends of the stack. With the sphere, it's just the same once more. I'm being resourceful because I don't have a compass either, so I'm using something from the kitchen as template for my circles. We need to rotate half a circle using the diameter as rotating axis to bring the sphere to life. So here's what I did. I folded my sheet of paper in four, traced the circle there and cut, to get 4 circles at once. Then fold the circles in half and cut again. Here's the rest of the process in a time lapse. The cylinder, the cone, and the sphere are the 3 rotation solids that are mentioned in the standards, which is why I chose to show those. However, if you have the time, or perhaps for your advanced students, experimenting with solids of revolution will really help exercise their spatial imagination. Let them come up with their own crazy 2D shapes and explore what happens when they rotate them. Challenge them to identify solids of revolution in real life and figure out what was the 2D shape that originated them. What happens if you rotate the 4th circle? How does the result change when moving the rotation axis away from the circle? That's all I have for today. I hope you find it interesting, and I'll be waiting to meet you and hear your questions and ideas at the unconference session. Goodbye and thank you.